everyone. I am Giulio, and thank you for the welcome. And today I wanted to yap about my little interest, sound chips and audio stuff, and vintage sound chip, what they make cool music, what's hiding inside of them. Yeah, you might already know that I like audio stuff, and stuff like synthesizers, audio effects, recording techniques, all sound chips, all the things that were used in video games and movie soundtracks. That fascinates me for a bunch of reasons. I think that one of the coolest one is that all of this tech that we use has deep ties with a lot of things, with computer science, with engineering, with mathematics, with physics, if we want to talk about audio and sound, but especially pop culture and history. I like to say this sentence that the instruments that we used directly shaped the music that we created, most of which still echoes today. To me, it's very interesting to know that some random guy in a studio in the 80s created a specific piano sound that then ended up on a very popular product that then ended up on some very popular music that is still played in clubs today. And knowing who is behind those things and what's behind those things fascinates me. And you probably think about vintage audio. That's probably the thing that you think about, like tapes, vinyls, vacuum tubes, all that kind of stuff that is associated with the imagery of vintage sound. But if you think about it, there is a lot more. There is all the digital stuff. There is all the computers and microcontrollers and things that we've been using since the 80s, basically. This thing here, for example, is one of the first samplers, the Faraday CMI from 1978, which was the first instrument that was able to record the barking of a dog and then play it back with different pitches on your keyboard. Or stuff like the DX7, that it was the brainchild of a random professor from university in America that discovered that you could create cool sounds by plugging sine waves one into each other. And this became basically a thing that now created dubstep and a lot of the stuff that we have today. Or if you think about it, sound libraries. Popular sounds like the A-main break or the Wilhelm scream that were recorded somewhere and then ended up being used in thousands of songs. And also audio processor effects, stuff that process your sound and give a special color to it. And those are a bit the forgotten ones when we're talking about digital vintage stuff. But I think they're very cool as well, especially since they have a history on their own. But the coolest thing about digital stuff, I think, is that it can be emulated. While an analog circuit or something like a tube amplifier, it's like something physical that is very hard to reproduce, like a violin from Paganini or something. No, that's the violin player. Forget it. Stradivari. Yeah, whatever. And there are very cool projects like MAME, which aim to collect as much software as possible and also the information on how to use that software, like how did the machine around that software work, and creating emulator for those things. And since they're digital, they can be emulated like 100% correctly. And so I was saying before that I like audio effects, for example, but what are audio effects? Here's a very nice demonstration of what audio effects are. We're talking about either physical or mathematical things that allow you to add some kind of processing to your sound. For example, delay, which works as an echo and repeats your song over and over, or distortion, which distorts like in a pleasant way your sound, or reverb that simulates the reverb of a room. For example, now if I scream into the microphone, I'm not going to do it, this room will probably reverberate, and with the reverb you can simulate those things. But how do they work under the hood? If we look at something simple like distortion, that sound like it's something that is very complicated, but a very simple model for distortion, it's basically amplifying audio and clipping the high and low part, like applying a clamp to it so that it always stays between 1 and -1. And this process of distortion, what it does is that it gives a lot of very sharp turns in an otherwise very smooth oscillation, which basically adds a lot of harmonics to it. And those are very pleasant, for example, for a sound like a guitar. And this is instead an effect that probably you saw even in your very basic Spotify player, the EQ, which is an effect that allows you to boost or remove the high and low frequencies or the middle frequencies. And how this thing works is really cool, because essentially you can represent most of the equalization with a formula that just includes sum and multiplication. The idea is that since an equalizer operates on frequencies, it basically depends on the previous values, and you can sum your previous value in certain ways so that you end up having more bass or more treble. And that way of representing EQ is basically how in DSP you do it, in which you can represent Z-1 means delay the sample by 1, and then you have sum, multiplication, and stuff like that. And then you have even more complicated effects, like reverb. And as I said before, reverb simulates the reverberation of a room. For example, it simulates the sound that screaming into a cathedral would make. But not only, it can also create stuff that is like very artificial, like it can simulate rooms that can never exist, like a reverb that is 70 seconds long. And to demonstrate the power of reverb, I just wanted to show you something. Has anyone ever turned on an old PlayStation 1? Probably a lot of people. The PlayStation 1 uses like an intro sound, which is a combination of different samples. And those samples have a reverb applied to them, which is done with a chip on the console itself. And that's how it will sound without the effect. It is incredibly dry. Let's try to apply some reverb to it. That's a completely different effect. And with this, I just wanted to showcase how, the effects are a bit forgotten in the audio history, but they're very important because they are basically what's changed something that is a bit weird to listen to something that is very pleasant and very interesting to listen to. And that's why I think it's quite fascinating how we develop those algorithms, especially since like we started talking about digital reverbs in 1961. This guy called Manfred Schroeder published this paper called Natural Sounding Artificial Reverberation, in which he described this algorithm that is virtually indistinguishable from a real room. Now that claim, it doesn't really hold water because like we're talking about technology from 61 and it sounds very metallic. But this is basically the same algorithm that the PlayStation 1 used and that a lot of even modern stuff uses. The idea is that you can give your your audio to a bunch of comp filters and then pass it to a series of all-pass filters in series. What does that mean? It means that we can make a reverb that is quite convincing how it sounds just by using some multiplication and a delay line, a circular buffer. And this is an extremely simple implementation of a Schroeder reverberator. Comp filter and all-pass filter are basically storing the old results and performing some multiplication on them. And then we just have a sequence in which first we put everything in parallel and then everything in series. That's a lot to understand, but the cool thing about this is that reverb basically is just sum and multiplication and the circular buffer, which means that all the magic is in the mathematics and that you can basically implement something that sounds like a real room in a few lines of code. or can you? Like, of course, this is an algorithm that was created in 1961, and the devil is in the details. We spent basically dozens of years trying to find a reverb that sounded convincing, and eventually we gave up, and now we use completely different technologies instead. And I think it's interesting. There is a very, very cool talk by a guy called Sean Costello that, if you're interested in reverb, I recommend you to watch. And he was talking about basically the academia was developing something related to reverb, like it was publishing paper on how there are like acoustical ways to make very realistic reverbs. And in the meantime, the industry was doing something completely different, because everyone in the industry was trying to make cool sounding reverbs, and no one was talking to each other, and no one was publishing paper around them. So there was this kind of mystery how the companies were doing it. And except a few people that were very chatty about it, a guy called John Datorro worked at, I think, Lexicon and then in Sonic. And he really liked what he was doing, and he really liked academia as well. So he just published a paper in which he was like, yeah, that's how we do it in the company. The company sued him, and turns out that if you are in Pennsylvania and you do work for hire, you are allowed to publish a paper about it. So yeah, a lot of stuff that we know nowadays, because companies are greedy, it's because of some guys that decided to yap too much. And this is how complicated a reverb can go. Like, this is a reverb from the beginning of the 80s. This is from a Lexicon unit. And this very weird graph that probably is overwhelming you and me as well, it's basically representing a big mathematical operation. And that's deep how DSP works. But let's go back a bit and let's talk about a bit about how we reach this point in the first place. This is arguably the first digital reverb or effect that was ever made. And this is the EAMT 250 by Electromess Technique, now called Barco. Someone probably heard this name. And this was made in '76. It costed a lot of money. It costed like $20K in 1976 money. So you can imagine how much is that now. And this was entirely built out of 74 series discrete logic chips. It used a bunch of deep packaged, I don't even think it was CMOS, logic ANDs, logic ORs, counters, multipliers, others, and stuff like that. So there was basically no microcontroller in here, because they did not exist for this kind of stuff yet. And it uses only 125 kilobits of RAM and 16 kilobits of program ROM. And it's run at around 20 megahertz. What is the coolest thing about this? This was used in a lot of very famous records. If you think about, for example, Give Me the Night by George Benson or Thriller by Michael Jackson, the engineers used this kind of effects. So this is very deep in pop culture. And that 16 kilobits of ROM, if you have that ROM now, you can basically execute it with an emulator and get the exact same sound that you will get from a vintage unit that now you probably can't even find anymore. Of course, you can do that if you know how the program is encoded. And there is this guy, David Morin, that spent a lot of time with his unit, with the schematics, and figured out basically how all the instructions are encoded. And you can do that because since they are all logic chips, you can just look at the schematic and see where stuff goes. You basically don't need to reverse engineer much. Fast forward 10 years. This is from 1986. This is the Alesis MIDIverb. This was a lot cheaper, and this was a hit. A lot of people got one of those. And this still used a bunch of logic chips, but it was a lot more integrated. And still, since it still uses logic chips, it means that if you have the schematic, you basically have the inner workings of the thing. In fact, we have the schematic, and someone created an emulator in JavaScript for it. So now you can go to this web page and input some audio and basically apply the exact same effect that this thing did on whatever random audio file that you want. I think that's pretty cool. Fast forward, actually around that time, the first DSP chips came out. The idea is that, as I said before, if you want to do effects, equalization, reverb, chorusing stuff, most of that is summon multiplication, done very, very fast. And if you had like a whatever microcontroller, even like the most powerful one, they were optimized for some things, but not for summon multiplication. So they could not do that very fast. They could not do that in real time. But the first DSP chips were specifically designed for that, like the TMS 320 or the Motorola 56K. And they could basically do all of those operations in a single cycle. And there is still documentation related to that. So you might think, well, if around that time there were a lot of different effects that were all built using DSP chips, like those single chips that do mathematics, does it mean that we can go and look at the documentation and just reverse engineer them that easily? Well, kinda. They integrated everything on those chips, and they even put those chips in stuff that was not even professional, like the Creative Sound Blaster AWE had a specific chip that could do reverb. And yeah, the question from before, if they're all using off-the-shelf chips, does it mean that we can just emulate them? No. Just here, just one of those units, the Eventide, was using an off-the-shelf chip. All the other ones was using custom chips, and except the Ensoniq ESP, because Datorro leaked the documentation, but we know that the guy likes to yap. And yeah, we have Alesis Roland that used Toshiba and Fujitsu gate arrays, the Lexicon that used a Motorola 56K, and 2 other custom chips. I have no idea what it's doing. Yamaha, of course, they did the FM chips, so they did chips for that as well. Why did everyone use custom chips where everything was like ready off the shelf? Because the chips that were ready off the shelf, they were very expensive. They costed like the equivalent of $50 back then. And like if you have very tiny margins and you want to make like something for mass production, that really impacts your production. And also because, as I said before, with those effects algorithm, everyone was very secretive about them. Like the product that they were selling was effectively software. So the hardware was just a mean to justifying that you were selling the software before software instrument existed. So it was a way of protecting their algorithms and intellectual property through obscurity. And they went through the lengths of designing custom chips just to do that. And how is it today? Today it's a tiny bit different. Like if you open a modern pedal, like Streamon, I think that's a Blue Sky, you will probably find a single chip and some RAM, and that's an analog devices Shark DSP. And the reason why they do that is because they don't care that much anymore, and sometimes they even just use an ARM microcontroller, so not even a proper DSP chip. And the modern chips have a lot of very cool features, like fuse that you just can blow, and then your software is locked in the chip, and it's basically impossible to remove it. So today it's not that much of a problem, but it's interesting to see how back then those things were being done. But what is a DSP anyway? What is the difference between an actual CPU? I made a bit of a table that is a bit like what ChatGPT told me. So the idea is that if you have something like a CPU, you have something that constantly branches all the time, and it does complex control flow, and it uses very large programs, like megabytes of code, and it's very optimized for serial generic execution. A GPU instead, it's extremely different because it does like a lot of data in parallel and basically no control flow. And DSPs are something that a bit in between. You have sometimes a bit of control flow, even smaller programs like 512 instructions, and they are what are called very large instruction word processors. Like a lot of time you have those, the DSPs have an instruction word that's like 5 bytes long because they're basically encoding a lot of stuff in them, because you can control every part of the microarchitecture just by changing what the instruction is doing. Something that you can't do on the CPU because the CPU manages that automatically, basically. And the most important thing that the DSP does are the MAC instruction, multiply and accumulate. Like as I said before, if you want to make an equalizer, like to boost your base, it's basically a sum and multiplication. So you want it on your DSP to be as fast as possible. And DSPs can do that instruction there, maybe even 32-bit of resolution in one single clock cycle. So they can do like millions of them per second, even more. And this operation, as I said, it's essential for a lot of audio stuff. Even like if you want to process signals that are phone signals, ADSL, they use for all that kind of stuff. Even we arrive at a point in which if you take a modern CPU, for example, the ARM CPU or even the latest Intel, and they say that you have DSP extension, they're basically saying that they are adding this instruction. Like like if they're saying that they're adding graphical extension, that's probably a matrix multiplication for 3D graphics. If they're adding DSP features, that's the thing that they're adding, because it's the most useful one, pretty much. And this is an example of a DSP chip. This is the Ensoniq ESP, the ES5510. And those are from the documentation that leaked because of that guy. And as I said before, we have a 48-bit instruction, so a giant instruction, in which you're basically, the first bit, you're saying the 2 inputs of the multiplier. The other bits, you're saying the 2 inputs of the arithmetic logic unit. The operand select, you're basically telling what the arithmetic logic unit should be doing. And the rest is like bits to control if you want to store or load. So these are like an incredibly simple instruction format in which you are basically telling every instruction what each part of the chip should be doing. And the idea is that with this chip you can implement audio effects very efficiently because you can just like tell it to do sum and multiplication and then tell it where do you want to store it. And all the fancy stuff that the CPU can do, like control flow, it's completely absent. The control flow, it's funny because it's handled with one single bit called the skip bit. Because with that bit, you can basically say, skip this instruction if certain conditions are met. And then there is like a documentation on what those conditions are. So you can't really jump between different parts of the programs. You can just skip certain parts. And that's okay, because this chip is especially designed to run the same program over and over and over and not change as much. Like similar to what the GPU is doing. So let's get to the core of this thing. My favorite company, Roland. Why? Because they made a lot of equipment that was used in a lot of famous pop songs, in a lot of famous soundtracks. For example, the Doom soundtrack was composed with the SC55. The MT32 was used for MS-DOS games. And the JP8000 was used in the Portal soundtrack and in the Half-Life soundtrack. They made a lot of cool stuff, and it really had a dent in pop culture. And they love to use custom chips, a lot of them. And they also don't love releasing emulators. and they also don't like people emulating them, but that's another discussion. And those are some cool chips that they made, and I even found some credits and some hidden in some ROMs. They made a bunch of DSP chips, the DSP, the CSP, the LSP, the XP, the ESP, and they all have slightly different features, and they were using different instruments. And I have no idea what those names mean, so I guess that's Luigi sound processor or something. The XP, they basically used that, and I think in 75 different products. They just made that behemoth of a chip that has like an internal DSP and can play 64 samples at the same time, and they use it in everything from like 94 to 2005, which I guess that they paid off the investment. How do we emulate them, since we want to preserve them? Well, we can do silicon reverse engineering, and that's a thing that I did for that unit there. The idea is that we can pour some acid on those chips and see what's inside of them. And then we can draw all the wires, reconstruct all the logic gates, and then reconstruct like a very precise schematics of what they're doing. And I did it for that unit that is from like 86, and it had 3 of those chips, and that took me a lot of work, but it worked. And let's try to see if we want to do that on the more modern stuff, like the ESP. This is the ESP chip that was used in a lot of stuff. Let's try to just, like, all those areas that you see on top and bottom are RAM, and that area in the center is all logic. Let's try to zoom in. That's a lot of logic. That will take you some time. Let's look at the XP. This is the one from the C88. Let's zoom in. Let's zoom in. I mean, the wires are clearly visible. If someone has a lot of patience, you can spend an entire lifetime in tracing them. But not me. I'm not doing that. I'm sorry. And plan B, poke it with a stick, which is exactly what I did. We don't destroy the chip. We keep it alive. And we send programs to it, and we see what it's doing. We can do that because DSPs are like CPUs. You can send a program and see what it's doing, and see the results of it. And I did this for the LSP, the chip that I was talking about before. Why? Because it was used the C88, and it's basically responsible for all the cool effects that they did back then, like the pitch shifter, the reverb, and like if we emulate this, we can do a lot of stuff. I didn't buy an C88 because I found that the same chip was using a very cheap other guitar pedal thing that I did. So that's one trick to save a lot of money. And first of all, we want to emulate the CPU of the thing, like the microcontroller. Why? Because that way we can see how they interact with each other. Like you can see the CPU talking to the DSP and see what they're saying to each other, and maybe check which program they're uploading. So this is the emulator. We can run it. And this is the same interface. And on this side, we can see that it's sending bytes to the DSP. And we can see what it's writing. And we can start to figure out how the host interface works. And then we can go here. And we can go into the configuration of that thing. We can switch between equalization, enhancer, spectrum, different effects. And we can see which bytes it's sending. And we can try to change some parameters, like the level of the bass and treble. And we're seeing that it's sending a lot of stuff to the DSP. And that will be useful for later. For example, this way I figured out that the CPU, it's uploading programs. The idea is that basically, if you want a specific effect to run, you have this program that does the effect, and you just upload it to the chip and let it run. Like what you would do uploading a shader to the GPU for 3D graphics. And by looking at those logs, it's telling you a few things. For example, that this DSP has an internal RAM, and it's 24 bits, and that it's always writing on that range from 80 to 200, suggesting that maybe there is something before. Like, why would they start from 0x80 if you can start from 0? Turns out that that thing will help us later. So with this emulator, we basically have a DSP program generator, a thing that just generates programs for that DSP that we want to emulate. So we can start changing the parameters, changing how much bass we want. And one cool thing that I saw is that every parameter was only changing the last byte. So what I thought with this is that, like, if it's changing just the last byte, it is like the equivalent of just changing the parameter of a function call. So that's probably telling us that the first two numbers are like an opcode, something that is fixed, and the last value is like a coefficient or an immediate or something that like gets sent to the operation. It's not something that like decides what to do, but which number to use. Then I said, okay, I kinda know what an EQ, like a bass, middle, and treble EQ should be doing. And if we know what it's doing, we can start making theories about it. Like, we see that there is a kind of load at the beginning. Then you see that there is that 28C0, 00C0, which is exactly the same thing that gets repeated after. So the same thing in two chunks with some different parameters. And then there are two different chunks which like look exactly the same. That might be in the 2 middle. And then the same thing gets repeated again for the right, like for the other stereo channel. This started to make sense. And I started to see which part of the program did what. Because, for example, if I changed the bass, only that part of the program changed. If I just changed the treble, just the second part of the program changed. So things started to make sense. So I looked at the first part, which I said, OK, that's probably the thing that it's loading the audio to then process it. So we can start to assume that maybe 20 it's the command for loading, and 7f it's the address, and 7f is a coefficient or something. We noticed that there is like something weird going on there, because there is like two knobs, 20000. And what I thought is that maybe that's a pipeline. Maybe like in MIPS processors, you need to put two knobs there, because otherwise you have a data collision, and you can't perform that operation immediately. And turns out that every time that every time that 8 command appeared, this one here, the 00 was always present. So it means that maybe that requires some pipelining. Then I tried to match this code, that was the one that did like the EQ for the bass, to something that, like I said, OK, that's probably how it works internally. That's the formula that it's using. So we can start to say, OK, the last one are the coefficients, because we already established those are the coefficients. And we can start to match those functions here and say, OK, that's probably multiply and accumulate. The other one is probably another multiply accumulate, and that's the third one. So it makes sense that maybe it's this formula here. And then I said, OK, but at the beginning I saw that 20 is load. So maybe 28 is some kind of different load. Turns out it's a load plus store. And it's doing that operation there. It's storing the resulting RAM. So this made complete sense. I knew how the algorithm worked, and I looked at the code for a DSP that should run that algorithm, and the thing started to line up. But this was not enough, because you can just make theories so much when you are not actually trying with the real hardware. So let's poke it with a stick. I did some very bad soldering to expose the host interface, and I basically used an Arduino Mega to just try to upload programs and see what it does. And So yeah, by writing programs from 80 to 200, that like the program area, and turns out that that area from 00 to 80 was always like filled with random stuff. So it turns out that it's like a working RAM where the variables are stored. And this means that we can check what opcode is doing. We can write a program that does something and writes to the working RAM. And then we can see what's the result of that. It's like the equivalent of running a program and make it write something in RAM and then check the result of the RAM. So that's what I did. I wrote this Arduino sketch with like clears everything, uploads a program via USB so I can quickly send experiments, and started USB and then immediately halted so that it runs like for one single cycle. And then it just dumps the content of the RAM to see what it's doing. So I did some tests. 20, 0101, maybe some kind of load. 08, 0000, bam, we got a 01 in the RAM. And so I figured out how the load and store works, which is like already a big part of the thing. And I like noticed that that 01 ended up every time in a different random position, which is like, what am I doing wrong? Well, it makes sense only if it's a circular buffer. Like it's something that when you write at position 00, you're not actually writing at 00, but you are referring to an offset. Like there is a buffer that constantly goes back and forth, and then when you're writing to 0, you're writing to the 00 compared to the current position. How did I test that? Put another load and store, and 00, 02, 00, 02. The thing made sense. It respected the relative position, but not the absolute one. So I spent too much time doing this, and I tried a lot of different opcodes, a lot of different combinations. I asked myself a lot of questions. How does loading and storing works? Is there more state that I don't know about? And end up doing this, a chart that tells you how the opcodes are formed. Turns out that we have two accumulators. There is another variable that I didn't know about, and you can either accumulate or store them, and there is also an absolute value there, and sometimes it's useful. That other part of the instruction is for storing into memory, and there's like one specific bit that performs a logic shift, and that other area instead it's used like as a position in memory where you want to store, and the last part is like 8-bit of integer sign coefficient. So like some example, if you have something like 000101, you're basically doing a +1. With 02, 03, you're loading all the immediates. With 05 instead, you are reading the memory and performing a multiply and accumulate. If you put a 20 instead, you are doing a equals instead of an accumulate, so you're loading something. With 40, you're doing the same, but with the other accumulator. A0, instead, it's like the absolute value to remove the sign. And you can combine a store with a load as well, if you use that bit there. There are a lot of different things that you can do. And so how did I figure out this? For example, there was another accumulator, and I didn't know about it. And how do you figure out if there is some state that you don't know about? Well, you remove power. What happens if you remove power? Everything gets corrupted. So it means that if you try something, and you unplug it, and then you plug it again, and it gives you a different result, maybe there is some internal state that you don't know about. And repeat this until you found a way to make it completely predictable. And so that's one thing that you can use to figure out if there is like some state that you don't know about. I then figured out the special instructions that there were as well, which you need. For example, read audio input, write to the audio output. The jump was so difficult, because then I figured out that I thought there was no control flow. Turns out there is. And how did I figure it out? I tried those instructions, and it seemed to be to like destroy the execution of the program for a bit, and then it worked again. And then I figured out that, of course, it destroyed. It was just performing a jump. That's why it disabled everything after it. So that's another thing that I discovered. But once we figured out all this stuff, this was finally enough to write an emulator. I wrote a C program that just received the DSP programs from the microcontroller emulator and just applied it to some audio. And I got the first effect working. Of course, not the most complicated one. Because if you want the more complicated ones, then there were a lot of things that still had to be solved. Like the 0x80 opcode seemed to behave completely randomly. I had no idea what it was doing. And there was some external RAM for reverbs and stuff that I had no idea how it was accessed. There is some weirdness going on with the pipeline. Like that if you perform a jump, it executes the following instruction and then it performs a jump, and that's the kind of stuff that gives you slightly different results, which are very different to debug. A lot of weird stuff going off with like sign and precision of the integer math. So at this point, for that instruction, the last one that I had no idea what it did, I went backwards and I said, well, this seems to be doing random stuff. Let's try to think, if we have those effects, what is the instruction that is missing? Like, if I want to implement something like a tremolo effect, something that changes the volume according to another parameter, how do you do that? Well, you multiply your thing by a variable. Yes, it's a multiplication per variable. Like that was the last thing that was missing. And that made sense because it was like the last opcode that was necessary to implement those effects in the first place. And the multiplication is weird. You basically have to load into a special variable by how much you want to multiply. And then there is a special opcode that you can use for multiplication. And the last number, it's like a parameter, like 09 does load, and 01 instead does increment. 41 instead first perform a shift left, a shift right of 16, and then does multiplication. You have no idea how difficult figuring out this stuff was and how many tries I needed to do. And then arrived the fun part, the external RAM. And now we were basically not able to just use the Arduino anymore. Now I needed to use a big logic analyzer, solder a bunch of wires to that poor RAM chip, and I then basically looked at the logic analyzer and looked at the addresses. The addresses is the most important thing because the data doesn't matter that much, because probably just writing some accumulator or something. The most important thing to get right is the address in which is loading. And the address were also handled in a pretty weird way. Like you could use the last bit of the opcode as a way to compute an address instruction by instruction. For example, you could do 0202 01 0003, and that will like keep accumulating the address to select a specific address. And then when you perform a special instruction, it will do the write or the read. So there was a lot of pipelining going on there as well. Like how I expect this to work is that probably inside that there is some ROM which works as like the microcode for sequencing the RAM stuff, because that's the only way that you can do something like that, I think. So it was finally complete, and it's on GitHub. That's been for a while. And now I was finally able to run all the effects, which I think they sound quite nice. This is the dry sound. And we can try it with the glorious long reverb. Or with other stuff like the pitch shift that changes the pitch of your sound. Or the last one, this is like a guitar multi-effect that like combined distortion with a delay, with a lot of weird stuff. That's nice. And that's always the same input sound. So yeah, now we have the emulator, and it's on GitHub. And it's a bit complicated to generate the programs right now because you need the other emulator, but then trying to like get a way to generate them with some other way that doesn't require running an entire microcontroller. And I wanted to make a plugin for this with Juice maybe, so that everyone could just use them on Logic, Ableton, Cubase, whatever. And yeah, that's the emulator. And or we could do something else. I wanted to put in a Raspberry Pi Pico because why not? Because we could make a guitar pedal with this. And but there is a problem. My emulator is slow. Like right now, I'm just executing an instruction per instruction, and basically it has to interpret everything, which is way too slow to be executing in real time. So I wondered, the program don't change, right? So we could do some very bad string concatenation and generate some C code from them. And so I generated this weird thing that takes the code for the LSP and generates weird C++. And before it was like slower than real time. And now I just try to run one compiled with -03. It's like 500x more faster than real time. And regarding the Raspberry Pi Pico, I tried to put it on Compiler Explorer, and it just generated me like 600 ARM instructions. That if you think about it, if you want to run at 48 kilohertz, you can basically have like 4,000 ARM instruction if you're running at 200 megahertz, like a Raspberry Pi Pico. And so it means that this can pretty much run. I tried it, and it was like 0.9x real time, so we're not yet there yet. And so that's why a very kind person just gave me a Raspberry Pi Pico 2, which I want to publicly thank here. And so I'm going to try to run it here. That probably is going to run a tiny bit faster, so that maybe we can make our guitar pedal. That would be cool, because we steal algorithms from companies, yay. And yeah, that's it. Thank you.
Yeah, thank you very much for this amazing talk. I certainly learned a lot, and we do have some time for questions, so any questions in the room?
Hey, would it make sense to like take multiple chips and put them into like one project, so you basically got like a master chip that you can like put in different projects or something like that?
What do you mean multiple chips?
Well, sometimes I would assume some chips maybe have the same functionality, and instead of having like different repositories for each chip, maybe you could like have like a universal one. Is that something you have planned?
I was thinking about it. The idea is that if you want to emulate a sound chip down to the host interface level, so like what the microcontroller is telling it to do, you need to have different implementations. What you can do is what basically MAME does, in which you have thousands of C++ classes in which like you emulate the sound chip, and the interface of the sound chip is basically just write at this address, load from this address, like what you would do at memory mapped.io. So like in my experience, so that like the sound chips, they are so different that you can't really generalize them, especially if you want to keep accuracy, but you can for sure like create something like MAME in which you have like all those different chips implemented.
I see, thank you.
Okay, anyone else?
Did you do this in your spare time, or did you get a grant or something?
in the tiny bit of time that remains after working over a long course of time, yeah.
You have mentioned the MT32, and I know that the MT32 uses LA synthesis.
Yeah, that's the LA chip, by the way. That's the MB87419. I don't remember, but that's the LA chip, yes.
Yeah, and I wanted to ask because I heard like because the LA synthesis is kind of special because it's not like a classic subtractive synthesis. Like, have you tried to emulate it, or is it too hard, or yeah?
Yeah, so that's a very good question because the LA synthesis is very cool because like the idea that there's 32 channels in which each channel can either be a PCM channel, and the PCM channel is actually played back in a very similar way to the MKS20, in which they are, I think they are storing the samples in an exponential format, so that way modulating the volume just becomes an addition. And then they use a ROM that is, I think it's this one to, if I remember correctly, that might be RAM actually, I don't remember, but it's basically they are doing the logarithm of the samples so that way they are turning them back into normal linear samples. They're also doing a lot of cool stuff with phase distortion, like they generate square waves with a filter applied to it by reading a sine wave table wrongly. And those are a lot of very cool things. There is how is it called? There is an emulator for the MT32, Munt, that emulates it very well. There is also a very hidden repository that I know about in which someone is reversing it from silicon by running the original MCS 96 called microcontroller of the MT32, but I think that he paused or he gave up or something, but there is a comment there that if you want you can try it. And so there is a lot of progress there. And emulating LA is cool because you can probably emulate the D50, which was like a much more expensive synthesizer. They use the same chip. But yeah, that's, I think, the current status of emulation.
I have another question, if it's okay to ask. I heard, I don't know the exact name, it's the Roland VP1000 or 5000, which I know...
is it the Vari phrase?
Yeah, which Daft Punk uses a lot. And are there maybe idea to use this one, or is it like another different glass?
I think it's I don't remember. It's for sure as a custom chip inside. Knowing that that's like from the 2000, it might be an ESP, and probably it also has an XV or an XP for sound playing. I have to look into the service manual. You can look at the model service manual and you can probably find the schematics and you can find exactly what it's doing inside. And then you can start making theories about it. But I have no idea.
Yeah, thanks.
Absolutely.
Do we have another question somewhere?
For like making the pedals or some, or like your own products out of the code, you basically reverse engineered. How much sense would it make to use like off-the-shelf DSP chips from the modern era now?
I think very little, for the simple fact that you can do the same on a microcontroller, and microcontrollers are like infinitely cheaper and infinitely easier to develop with. Yeah, you can try it on a Raspberry Pi Pico. If it doesn't work, you can get a Teensy. If that doesn't work, you can get a Raspberry Pi. And those are like an order of magnitude easier than just finding a DSP and make it a PCB for it or using a DSP dev board. I think that we are arrived at a point in history in which if you need a DSP, you're probably making a rocket. I don't know.
Thank you.
I'm not an expert anyway. I'm just doing stuff with electronics. I'm a computer scientist. But yeah.
Do I see another question somewhere?
There, down there. There is one hand.
Oh.
When you decap, what was it called? When you look at the silicon of a chip, you showed the pictures of like the super complex circuitry. Is there some way to automate the tracing of that?
I would love to. Yes, I know a guy that is doing some very cool stuff, especially with his chip. And the idea is that you can use the microscope and the focus of the microscope to eliminate certain areas of the chip. The idea is that if those are multiple layers of metal and polysilicon, what you can do is that you can focus the microscope in a specific way so that everything else is blurred and you get only those wires in focus. And that way it becomes incredibly easy to run like much simpler algorithms, such as like even not even machine learning stuff, even stuff with OpenCV, to just extract their wires. So the idea is that yes, you can. And the other thing that you can do is that you can train a machine learning model for segmentation, and that's what I've been trying to do just to figure out the stuff. All the other lines that you see here, those are all standard cells, which are the actual logic gates. And the idea is that sometimes are very occluded by wires, and you need to look at what's happening under there to figure out, yeah, okay, I have something connected. What is it? Is it an AND? Is it an OR? You can probably guess, but it only gets you so far. And you can see like in some areas like here, it's like completely occluded, so it gets really difficult. What you do in those cases is called lapping, which is like putting the die on a machine, which uses some extremely fine sandpaper to remove the top layers so that you can then see what's underneath. But again, I'm talking out of my something because that's just stuff that I heard from people, because I never actually did this. I always got other people to do it for me. But those are the things that you can do, I think.
Cool, thanks.
Okay, we got time for at least one more quick question. If there isn't one right now, then I would ask you to give him another big round of applause. And if you come up with other questions,
thank you.